Alright, we're going to do some examples using identities to simplify. We're starting with tangent x over secant x. Notice how I'm not using a Greek letter for the angle. Sometimes we use x, sometimes we use t, sometimes we use a Greek letter. They're all variables, so just adapt, be versatile, really, right? Okay. Okay, so let's go ahead and change everything to sines and cosines. Okay, so what is tangent changed to sines and cosines? Okay, so we're going to change tangent to sine x over cosine x. Alright, what is secant changed to sines and cosines? 1 over cosine. So now we have a fraction divided by a fraction, so we can do the little thing we learned called copy dot flip. Very good. Whoa. I'm writing down the wrong thing. I guess I could have gone with that, though. Sine x over cosine x times cosine x over 1. So I wrote down the top fraction as is. I'm going to multiply, and I flip over the bottom fraction. But you might notice even before you start trying to multiply them, what ends up happening? We would have cosine over cosine, which is 1. So it doesn't even need to be there. So our final answer would be sine x over 1, which is simply what? There's our answer. These are kind of like little proofs, sort of, or we're leading up to that. Sine x plus cotangent x cosine x. There, that's what we want to simplify. So again, we're going to use the same hint. This is a very valuable hint for a lot of this type of problem. Change everything to sine or cosine. So sine is already sine, right? Can I change cotangent so it's in terms of sine and cosine? Okay. So cosine x over sine x for the cotangent part of it. But then that would just be multiplying times cosine x, because that's already in terms of sine and cosine. Okay. Well, there's this obvious simplification we can do here where we change this to cosine squared x over sine x. Now, it's too bad that this is just a sine x and not a sine squared, because if it were a sine squared, then sine squared plus cosine squared equals 1. Ooh, so maybe get a common denominator would be a helpful idea, right? Hint, common denominator. There's not two sides. We're simplifying. If it's an equation, you can multiply both sides by something. But this is not an equation. It's just an expression, and we're simplifying it. Okay, so what we can do is get a common denominator here, like Alicia suggested. So to get a common denominator, we would need sine x on the bottom, but in order to do that, we have to multiply the top and the bottom, so maybe put that over 1. Multiply the top and the bottom by sine over sine, right? Does that give us a common denominator? So then we would have, I'm not getting a response, so I'm worried I'm moving too fast, but I also don't want to waste our time. So slow me down if you need me to. If they have a common denominator, can we now add those two fractions together? So when you're adding fractions, the denominators have to be the same, and the numerators just add together and the denominator stays the same, correct? So you end up with sine squared x plus cosine squared x over sine x. Okay, so then this is what identity? Sine squared plus cosine squared? That is the Pythagorean identity. So that ends up equaling 1 over sine x because of that identity. And what's 1 over sine x? Cosecant x. Can you believe we turned that ugly thing into this simple thing? Second to last step. Where?
One below.
Right here?
Yes.
Okay. So this thing right here, okay, so how did I get to this step or from this step?
From that.
Okay. So I added these fractions together and I got sine squared x plus cosine squared x. And that is equal exactly to this Pythagorean identity, although we used alphas instead of x's. So the sine squared of a certain angle plus the cosine squared of that same angle always equals 1. And we proved that with Pythagorean theorem. So we know it's true. So since that identity is true, we can simply replace sine squared plus cosine squared with 1, because that's what it equals.
Okay.
And then this is just a reciprocal identity.
Okay, that makes sense.
Here, do you guys want to try one? See what we can do with it on your own?
Yes.
Okay. Yeah, pretty much. Not always when we get into the other sections, but most of the time, that is a very good thing to start trying first. So there, try that problem for me.